Let's talk about proportionality. We say that two things are proportional to each other if they're multiples of each other. So two quantities that are one is twice the other, twice as big as the other, or 3 times as big as the other, or 4.5 times as little as the other one. Mathematically, we write that if A is proportional to B, then A equals to K times B, where K is some constant, positive constant. Notice that while it should be positive, it need not be an integer. So you could have two proportional things with a fraction in the middle, like 4.5 or 5.3. If we were to draw this relationship, you would notice that it's actually linear. So if I were to draw A equals KB, or if I relabel, and it might be easier to see, Y equals K times X, or maybe for a particular example, Y equals 2X, let's say, you know that if you draw it on the XY axis, you're going to have a line. Now, this constant K is also sometimes called a proportionality constant. And the next question is, if we take two things that are in proportion and therefore are linearly connected, what will happen if we apply a power function to both of them? Will that proportion stay the same? Will it get bigger? Will it get smaller? What will happen to the proportionality constant and just the relationship as a whole? So let's take a first look at our example here. A basic physiological principle is that the strength of a muscle or bone is proportional to its cross-sectional area. So cross-sectional area meaning what the bone or muscle looks like if it was cut. If an athlete's muscle grew to double its radius, how much has the strength increased by? Okay, so let's first of all translate some of the information we have into our proportionality relationship. The notation for this also, I should mention, is this. A is proportional to B. We denote that by the little sort of Jesus fish sign. Okay, so the first sentence here says that the strength of a muscle is proportional to its cross-sectional area. So as a shortcut, we can say that the strength is proportional with our little proportionality symbol to the cross-sectional area. And then we're given some information about the athlete's muscle that grows to double the radius. So there's an implicit assumption there about the shape of a muscle. Now, if you think of some of our bones or some of our muscles, some of the biggest ones in our body, it is a fairly reasonable assumption to make that the shape is going to be cylindrical. Think of the bones, for example, in your arms or the muscles in your arms, right? Of course, at the beginning, at the end, they might be narrower or wider, but for the majority of their length, they're fairly cylindrical, okay? So this is one simplifying assumption that we're going to make here, which also, though, means that all of our conclusions are going to be about bones or muscles that are cylindrical in their shape. Now, the radius here, of course, is then this little guy, and the cross-sectional area is going to be a circle. Now, the good thing about that is if we already know the shape, then we should be able to write down the actual formula for the cross-sectional area. In our case, it's a circle, and the area of a circle is pi r squared. Okay, so then the next thing we know is that the muscle has grown to double its radius, and what we're wondering is how did that affect the strength? So let's say that my old strength or initial strength, is then of course proportional to the initial radius, so pi r squared, whereas the new strength that the muscle has is now proportional to the new radius that is double the old radius. Okay, so this is a very important thing to notice here is that, so I can say that it's proportional to the new radius, r new squared, but I also know that my new radius is double the old one. This is the proportionality of the radius. Okay, so this new radius is actually twice the old radius, and I can replace that in the formula. So I have pi twice my old radius squared. And you guys are going to do a bunch more examples in class, but it's essential here to recognize that the new double the radius replaces the entire old radius underneath. So this is where r used to be. So the whole thing has to now be squared. Okay? And then the exponential laws dictate that the power has to come down on top of everything. So I'm going to have pi times 4r squared. Right? So now, if I just move the 4 out to the front, I have 4 pi r squared here. And what I would really like to say something about is how much has the strength increased by? So I'm not just talking about what the new strength is, but rather how much has it increased by? So what is it in comparison to the old strength? So I'm going to take a closer look at my new strength, expression for the new strength, and expression for the old strength, and ask myself, how do they relate? Can I see the expression for the old strength in the new one? Sure, it's 4 pi r squared, right? So this pi r squared is exactly my initial strength, which means that this factor of 4 is exactly how much bigger new strength is compared to the previous strength. So as the conclusion, I can then state that the strength of the muscle has quadrupled. Let's now take a look at another example to see how proportionality gets used in applications. Estimating the mass of extinct animals is very difficult because we have to base our entire findings on the skeleton alone with no knowledge of the animal's muscle mass. So for example, given a skeleton of a saber-toothed tiger, one can only try to imagine what it looked like in real life. And you can imagine different kinds of things. Did it look very muscular and built? Was it more similar to a current living tiger? Was it more like a bear? Or was it more like a really adorable house pet? Thankfully, biologists have developed a number of different allometric or power relationships that are essentially proportional relationships to describe the variety of relationships within the body. In our case, the one that's going to be useful is some kind of relationship that connects a major bone length, for example, with the body mass or muscle mass of an animal. So let's take a look here. The relationship that we're going to use is exactly that. The body mass and skull length are related via this power relationship here. Notice a really small difference is that our power in this case is not an integer, but that's okay because we're not going to actually sketch it. We're just going to use it to derive the actual numbers. The units here are body mass is in kilograms and the skull length is measured in millimeters. So this is the skull length, this is the body mass that it produces, and K is some kind of proportionality constant. We are given some information about one of the current living animals that sort of belongs to the same type of family of predators as a saber-toothed tiger would. Right? So we're given the information about a gray wolf's body mass and its skull length in order to help us actually solve for this proportionality constant. So let's take a look at the first question. The first question asks to find the weight of a saber-toothed tiger whose fossils that you've managed to dig up maybe in your backyard, if you're lucky, have a skull length of 350 millimeters. Okay, so let's take a look at part 1 here, and let's use or try to use our formula immediately, directly. So I know that my relationship between the body mass and the skull length is given by this formula. So the skull length of the fossil that I have on hand is 350 millimeters, and I would like to figure out what is the body mass that corresponds to that skeleton. Now the problem, of course, is this proportionality constant k I have no value for yet. And that is what I'm going to use the gray wolf information to figure out. Okay, so for the gray wolf, what we have is the exact same relationship. And again, we're assuming that these animals are related in some way. So what works for the skeleton and the body mass of a wolf would also work for the skeleton and the body mass of the saber-toothed tiger. Okay, so for the wolf, I have the exact same formula, except in the wolf's case, I know that the skull length is 275 millimeters and the body mass is 45 kilograms, which means that I only have one unknown in this equation and I can directly solve for it. Okay, take a minute here and actually try to solve this for yourself. I'm going to write down the answer, but please make sure you're actually able to follow through these steps. Okay, so here k would be 45 divided by 275 to the power 3.13. I'm not going to bother computing this as an actual decimal. Feel free to do so if you would like. I'm going to leave it like that because I'm not quite done yet, right? The question was asking to compute the weight of a tiger, so I have to plug this value of k back into my formula here in order to figure out the actual body mass of the tiger. Okay, let me just rewrite this further down. So for saber-toothed tiger, what I have is b is equal to k, which is the value I just found. So again, feel free to compute that as a decimal. I'm not going to bother. So that's the k times, just checking the formula, x, which is the skull length. And for the saber-toothed tiger's fossils, we have 350 to the power 3.13. Okay, so just to be clear here, this is my k, and the rest of it comes from the knowledge of the measurement of the skull length of the fossil. And if I compute this number, I'm going to get approximately 96. As this is a word problem with units, your answer should also contain units. So let's take a look here. When given the skull length in millimeters, the body mass will come out to be in kilograms. So this will be in kilograms. The one biggest upside of having a word problem with context, particularly the one that you can relate to, is that you can check whether your answer makes any sense at all. So here, a gray wolf had the skull length of 275 and the saber-toothed tiger fossils had a skull length of 350. So you expect that the body mass of the tiger would be bigger than 45, which corresponded to a smaller skull length of the wolf. And indeed, we end up with 96. Now, sometimes power functions can be misleading like that because 45 to 275 is not quite the same as 350 to 96 because they're not in direct proportion. They're related through this power of 3, which means that a difference between the skull length will be actually magnified to correspond to a larger difference between the weight, right? But if you did get a number here that is less than 45, this is when you should be concerned because that is not at all what we expect the amount to be. If you get a negative number, don't just take an absolute value of it and move on with life. The math should support the context, not fight against it. Now, for part 2, we're asked to find the skull length of the saber-toothed tiger of a weight of 80 kilograms. So if an animal like that lived and weighed 80 kilograms, how big should we expect its skull to be? Now I'm going to leave you to do this part. You're going to work out through the exact same formula where the value of k is the one that we have just found, okay? So make sure you use the exact same value of k for part 2. Now, for this lecture, don't forget to do your pre-lecture assignment on WebWork, and we'll do more applications like these with proportionality and power functions in class.